So Avogadros Law states that the volume of a gas maintained at constant temperature and pressure is going to be directly proportional to the number of moles of that gas. So the proportionality that we see here indicates that your volume and your number of moles are going to be directly related. So if you double the number of moles in a container and maintain your temperature and pressure at a constant value, you should see a doubling of the volume of your gas. And basically that relationship is what Avogadros Law entails. Now, Avogadros Law is connected to Avogadros' hypothesis, which says that equal volumes of gases at the same temperature and pressure contain equal number of molecules. And so we know that there's a relationship between the volume of a gas at STP and the number of molecules. So you guys have seen this 22.4 liters per mole value. Okay, so at STP, there are 22.4 liters for every 1 mole of that gas. So Avogadros' law is connected to Avogadros' hypothesis, which would say that 22.4 liters for every 6.022 times 10 to the 23rd molecules at STP is how this relationship would look. But because Avogadros' law considers molar amounts, we look at it with respect to 22.4 liters per mole. So when discussing problems with respect to Avogadros' law, we can obviously discuss it with respect to moles, right? So if we look at the equation that we have down here, obviously we have 3 moles of this H2 gas for every 2 moles of the ammonia that's produced. We can also look at our moles with respect to being volumes. So we can say, hey, there are 3 volumes being taken up, okay, in terms of our H2, and that gives us 2 volumes of our NH3 product. Okay, so you can look at these problems with respect to moles, you can look at them with respect to volumes, but they're kind of interchangeable. So if we go ahead and we look at this problem here, it tells us that ammonia burns in oxygen to form NO and water vapor. And so what they want to know is how many volumes of NO and H2O are obtained from 1 volume of ammonia at the same temperature and pressure. Okay, so they've told us we're at the same temperature and pressure, so we know that Avogadros' law will hold true. Okay, so your volume and your moles are basically proportional. So if I know I have 1 volume of NH3, they want us to indicate how many volumes of H2O and NO are present. Okay, so this is what they're trying to get us to figure out. So how do we look at this? Well, first of all, we're going to consider the information given to us in the balanced equation. Okay, so if we look at this equation, we have 4 volumes of NH3. Okay, so for every 4 volumes of NH3, we're going to get 4 volumes of NO, okay, and 6 volumes of H2O. Okay, so this relationship obviously is connected to the mole amount. So you can look at it however you want. In this case, they're asking us in volumes, so we're going to express our answer in volumes. So because there is a 1-to-1 relationship between NO and NH3, 1 volume of NH3 is therefore going to give us 1 mole of NO, or 1 volume of NO, I apologize. So if we use the relationship that we have, okay, we can see what cancels, boom, boom, okay, and that's going to give us 1 volume of NO. Okay, in that same approach, we can look at the number of volumes of H2O that we're going to obtain. So once again, we start with 1 volume of NH3. Okay, the relationship between NH3 and H2O is 6 to 4. Right, so we have that relationship. Okay, so that 6 to 4 relationship times 1 is going to give us 1.5 of volumes of H2O. Okay, so our volume of NH3, volume of NH3 cancel, and that gives us our corresponding values. So I hope that you're seeing the relationship between your volume and your molar amounts, right? They're proportional. We're doing these calculations with volumes, but as you can see, they're directly related to your number of moles. So it's just a really straightforward approach.